Today we're going to be solving exponentials, and in order to do that, we are going to start with the basics. So up here on the top, it tells us to solve for any unknown in a simple logarithmic equation, begin by converting it to an exponential equation. If we have an unknown in the argument, we're going to want to convert that down to an exponential in order to free this argument. So we get 4 cubed is equal to y, which we can simplify. If our unknown is over in the end here, we can convert that to an exponential by dropping the base and switching those, and we get 4 to the x is equal to 64. Then we can do common base there to find our answer. And on our last one, if the base is the unknown, we drop the base and then switch these, and then we can do a radical in order to solve it. So just like we've done with the logs where we're looking for our missing piece, that's the same thing we want to do with the exponential. That definition is crucial to be able to convert from an exponential to a log. Some of the things that we do need to know: the value of a logarithm blank equal to the exponent of the corresponding exponential equation. That is always. The value of a logarithm is always equal to the exponent of the corresponding exponential equation. So for our diagram here, that means that the value of the log, so this part right here, is always the exponent. That is true right there. The argument of a logarithmic expression is never a negative number. The argument is this part right here. That is never equal to a negative number because that is the value of an exponential, and we know we can't have a negative for an exponential. The value of a logarithm is blank equal to a negative number. So our value of a logarithm, this part right here, can be equal to a negative number, so this is sometimes. The base of a logarithm is a negative number. That is never true. The base of a logarithm is the same as the base of an exponential. So it can never be a negative. And the base of a logarithm is blank equal to 1. Well, that would make this the base of 1 as well. And if we had a base of 1 here, it would be a horizontal line, not an exponential. So this also would be never. So we cannot have a negative base. We can't have a negative argument, because that comes from the value right here, which is never going to be negative. Now, in order to solve these exponentials and logs, this definition is really important. And so we've seen it a couple different ways. You can drop the base and switch these. That allows you to go between the two forms. Or some people will do it with this circle part. So the base with that exponent is equal to that value. There is some way that you're going to have to learn to make sure that you can convert that from a log to an exponential and from an exponential to a log, because that's a crucial part of solving. We'll start with some of the easier ones now, and then we'll move to some harder ones. We'll start here. Our unknown is in the exponent. So in order to solve this one, we're going to have to free it out of the exponent. To do that, we use our definition. So we drop the base, so we get a log with a base of 7. The base on the exponential and the log is always the same. And then we switch these. So we get log base 7 of 5 is equal to 3x. Our last step is then to divide by 3. Now, all of this is one term, so you're not dividing the 5 by 3, you're dividing the entire thing, the log base 7 of 5. Now, that's something you can put into the calculator. So I'll put that here. In your calculator, you're going to hit alpha window and go to the log base. We put in our log base of 7, and then our argument of 5. And then we get out of the argument, so we're going to go to the other side of the parentheses and divide it by 3. When you write these answers down, you're going to want to keep at least 2 decimals. Sometimes people will keep 3, so 2 or 3 is what you're looking for. So 0.276 would be my answer. And we have solved that exponential. All right, we'll try another easy one here. We have e to the x minus 6 is equal to 150. Our variable is in the exponent. X is in the exponent. The only way of freeing this out is using that definition. So we're going to convert this to a log. I drop the e, and we know that a log with a base of e is the natural log. And then we switch those, so we get 150 is equal to x minus 6. My last step would be to add the 6. Again, this is all one term, so you're not adding 150 plus 6, you're adding the natural log of 150 plus 6. So in our calculator here, the ln button, the natural log, is to the left of 4. So I hit natural log. Go. 150, I make sure to close my parentheses because that's the whole entire term there. And then we're going to add the 6. Again, we want to keep 2 or 3 decimals. So we get x is approximately 11.011. All right, now we're going to move to some a little bit harder here. This has more steps. That's why I say it's a little bit harder. We do not use this definition until we're ready to free it from the exponent, which the x value is in the exponent here, but we can't use that definition until this term is completely by itself. So we've got a few more steps to do here. The first thing I would want to do is move everything away from it. So we've got this plus 1, so I would subtract 1, just like you've solved in the past, trying to get that x term by itself. That gives us 1/3 times 6 to the negative 4x is equal to 5. Our next step is to get rid of this 1/3 so that we're leaving this term by itself. We want to isolate it. So I'm going to multiply both sides times 3 to get rid of the 1/3. That will cancel it there, giving me 6 to the negative 4x is equal to 15. Now we're ready to use the definition. That's when you use it. When it's isolated, it's completely by itself. So we use our definition. The base on the exponential is the base on the log. So we get a log with a base of 6. And then these two switch, so we get 15 is equal to negative 4x. My last step is to divide by negative 4. And that's something we can put in the calculator. So we'll put that part into the calculator. Go. Alpha window gets me that log base. 6 goes into the base. 15 is my argument, and then I make sure to get out of the argument. And then we're going to divide that by negative 4. And so we get negative 0.378. You can always check your work by plugging this part back in. You would want to use the entire thing in order to get the exact answer. All right, we'll look at a couple more with more steps there. So on this one here, my first step would be to get rid of this minus 5. So I add 5. We get 4 to the x minus 3 is equal to 21. Now we're ready to convert that to a log. So I get a log with a base of 4. Remember, the base on the exponent is the base on the log. And then those switch, so we get 21 is equal to x minus 3. That frees this from the exponent. My last step would be to add 3. You are not adding that 3 to the 21. You are adding that 3 to that entire term. That is one term. So when we put this in the calculator, we're going to hit alpha window, log base. The 4 goes in the base, the 21 goes in the argument, and then plus 3. You could do that in Desmos as well. So when you go to Desmos, you're going to go to that function keyboard, and it will give you the log so that you can replace the base. Remember, when you're using this log down here to the left of 7, that is a base of 10. Anytime you push this button right here, it is a base of 10. And when you push the natural log one, it is a base of e. So keep that in mind. That gives us 5.011. 0.196. All right, for our next example here, again, we've got a couple steps before we can get started with that definition. We've got to get this portion by itself first. We want to get that isolated. So we're going to subtract the 1 to get it to the other side, and we get 2 times 3 to the 5x equals 54. I divide by 2, and we get 3 to the 5x is equal to 27. Now we're ready to either use the definition, or last class we did solving by common base. So I want to show you, I'll go ahead and redo that one just to remind you. Both of these can have a common base. So if you recognize that at this point, then you can go ahead and change that to a common base. 27 is 3 to the 3rd power. And so 5x is equal to 3. And we divide by 5. And we can leave that as a fraction, or you can convert it to a decimal, whichever one you prefer. All right, in the previous module, we talked about compound interest and growth and decay exponentials, but we didn't talk about solving them. We were holding that for module 7. So now we can actually solve those equations that we wrote and used in the previous module. So we're going to do that. Suppose $4,000 principal is invested at 6% interest that is continuously compounded and yields $5,333. For how many years was it invested? All right, so we want to solve this problem here. As soon as we see continuously compounded, we know to use the PERT equation. So I know I'm going to start with A equals P times E raised to the RT power. It told us that the amount at the end was 5,333, so I would put that in the place of the A. We started with 4,000, so I'm going to put that in the place of the P. E is a number, not a variable, so that stays as E. My rate was 6%, so I need to change that to a decimal, so that would be 0.06. And the T is what we do not know. Now we're ready to solve this. So we just learned that we want to get this part by itself. We want to isolate our exponential part. So we divide by 4,000. Since these two are being multiplied, I'm going to divide to get it to the other side. Now, when you're working these problems, you want to make sure that you are not rounding until the very end. So use the entire thing that the calculator says. When we get this, we want to use this entire thing. We do not want to round until the end of the problem. So 1.33325 is equal to e to the 0.06 t power. Now we're ready to convert this to a log in order to free my t. So the base on the exponential is the base on the log. So this is going to be a log with a base of e, which is the natural log. And then they switch, so 0.06t is going to come to this side, and this is my argument, 1.3325. My last step, these two are being multiplied, so I'm going to divide by 0.06. All right, so here we go. Oops, you can't see that because of the glare. There we go, that's a good place for it. All right, so we're going to do the natural log, and I can just go ahead and use my arrow and copy and paste that. So if it's a long decimal, you don't have to worry about rounding because you can copy and paste it. I highlight it, hit enter, and it will copy it down there for me. And then I close my parentheses and divide it by 0.06. And so there is our answer, 4.79 years. Oops. All right, we're going to look at another word problem here. It says Newton's law of cooling states that for a cooling substance with initial temperature T naught, the temperature T after T hours can be modeled by this equation. Lots of T's there. So T here is the final temperature. T naught is the initial temperature, so this is going to be my initial temperature. TR is going to be our surrounding temperature. R is going to be that rate, and then this is my final temperature. All right, so it says, a corpse was found in a motel room with a bullet lodged in it. At the time of discovery, the temperature of the corpse was 80 degrees. Given that the room is kept at a constant temperature of 60 degrees and that the body's cooling constant is R equals 1.438, how long ago did the person die? So some forensic science here. So our temperature, our final temperature was 80 degrees. So we're going to have that 80 degrees at the end here. Now we're going to set up the rest. So our T naught, our initial temperature for a body, we're just going to go ahead and use 96.5 minus our surrounding temperature, which is 60 degrees. And then E, remember, is a number, not a variable, minus our cooling rate of 1.438. We don't know the time, so that's going to stay as T, plus our surrounding temperature again, which is 60. So we've used the formula here. Now we're going to go ahead and simplify this. 96.5 minus 60 is 36.5. Our first step in solving this is going to be to subtract the 60. That gives us 20 is equal to 36.5 times e to the negative 1.438t. We now need to get rid of this 36.5. So it is being multiplied, so we divide by 36.5. Again, we don't want to round this to the end, so you want to keep that value. When I put it on my paper, and I ran out of space here, I can go ahead and put 0.548 is equal to e to the negative 1.438t. So I did round it to write it on my paper just to not write all of these decimals, but when I do the actual calculation, I will use this entire thing. So now we're ready to convert this. E is my base, so I'm going to make this a log with a base of e, which is the natural log of this 0.548 is equal to negative 1.438t. All right, so when I do my last step here, I'm going to divide by negative 1.438. And now it's time to put this in the calculator. So I don't want to round when I do this on the calculator portion, so I'm going to hit the natural log. I'm going to use the arrow to copy that. And then my last step is to divide by that negative 1.438. And so we get 0.418 hours. So that is less than half an hour. So they've not been dead for a very long time. All right, we're going to look at one more question that's a little bit challenging. It says an amount of radium is stored in a container. The amount Y in grams of radium present after T years can be modeled by Y equals C times E raised to the negative 0.00043T. What is its half-life? We had defined its half-life as the time it takes in order to get to half of its initial amount. Since they're not giving us a lot of information here, we really need to think through this problem. So we are looking for the time that it takes to get to half of its initial amount. Well, the initial amount is always that first part right there, that's C. And so half of C is what we're looking for. We've got a lot of variables here, so we need to get rid of it. Since we've got the C on both sides, if I divide by C here, that cancels out on both sides. And so we get 1/2 is equal to e to the negative 0.0043 t. Now we're ready to convert it to a log. So I drop the base. That gives me a natural log of 1/2 is equal to negative 0.00043 t. And my last step is to divide by that negative 0.00. Sorry about that, writing pretty small here at the end to get through my paper. So we went with half of the initial amount. The initial amount was c, so we got half of c right here. We divided by the c, and it canceled out on both sides, leaving me with the only variable of t. I drop the base, and so that gives me a natural log of 1/2 is equal to this, and I'm going to divide by that negative 0.00043. Now, when we put this in our calculator here, remember that is the natural log of 1/2, and then close the parentheses, and then divide by that negative 0.00043. If you do not close the parentheses there, it will divide the 1/2 by that, and all of that is one term. So the half-life on this is 1611.97. That is a lot of years. 1611.97 years. So now you know how to solve exponentials using algebra.